And the topics we plan to cover today are listed here on this slide. So we'll start with CAD geometry and file formats because that's going to be the starting point of any of your machining operations. And then we'll talk a little bit about machining tolerances, the role of stock to leave, and how to control surface finish. And we will walk through all of these things during the demo sessions. And once we've covered those areas, what we will go ahead and do is to talk about general machining strategy, the different operation types, and toolpath containment strategies. So what we will do today is we will go ahead and I will speak to the content on the slides and then turn it over to Uday for a demo. So it will be a interactive process where I will provide some information initially and then Uday will go ahead and do the demonstration. Okay, so let's get started with the first topic, which is CAD geometry types. As the person responsible for machining, you are probably going to be receiving geometry in many different formats. So we are covering the major formats on this slide, and we'll talk about each one briefly. Solids are created by CAD systems such as SolidWorks and a Libre design, and a solid is a collection of surfaces which is a watertight volume, and the mating surfaces share edges with each other so that there are no gaps. And so a solid model is probably the most accurate representation of the geometry if it is available for you to start for your machining process. The next type of geometry is surfaces, and surfaces are a mathematical representation of the geometry, and you can have the mathematical representation cover standard shapes like plane, cylinder, sphere, torus, etc. But you can also represent sculpted geometry or free-form geometry. So for example, if your CAD system is a free-form modeler like RhinoCam, what you probably have there are what's called NURBS surfaces, non-uniform rational basis splines, which is just a very accurate mathematical representation of the geometry. And surfaces can either be free floating or they can be linked together to form what we call polysurfaces. So the surfaces would be a second type of geometry that you might receive in order to start your machining. The last type that we will mention here are meshes. Meshes are essentially a polygonal approximation of the geometry. One example of where you might receive meshes is, for example, from scanned data. And one thing to keep in mind is that mesh geometry can be data intensive in terms of calculations. And also the accuracy of machining cannot really be controlled or improved beyond the accuracy of the original model. And so when you think about geometry, solids would be the preferred option if it is available to you, followed by surfaces, which are accurate mathematical representation. And your last option would be meshes if there is no other way for you to receive the data to start your machining process. Okay, so having talked about the geometry, let's talk a little bit about file formats. If you have the ability to receive the file in a native format, that would be your best option because there is no translation involved. And when we say the native format, what we mean by that is, for example, in a CAD system, for visual CAD/CAM, you have the .vcp files. For Rhino, you have the .3dm. SolidWorks, you have the .sldprt files, and then for a LibreCam, you have the .adprt file. So if, for example, you were using our plugin for SolidWorks, then you would want to work on a SolidWorks solid model. And if you're using Rhino, it's going to be the Rhino NURBS surfaces that you'd be working with. So files created by the host CAD system, if they're available to you and if you're able to machine using those formats would be the preferred way to go. If you do not have the option of doing that, you could then receive file through data exchange formats. There are a couple of formats. We'll talk about the step files first. This is a newer protocol, and it is a better representation of the data that is imported from a CAD system. And so the reason the step file is a better option than IGES is that it has topology information. Remember, we were talking about topology being how surfaces share edges and are interconnected so that there are no gaps. So the step files would be a better solution in terms of a data exchange format. If that's not available, you could also certainly work with IGES files. And on IGES files, you have essentially when you import data from a CAD system, you do not have topology information, and the surfaces are free-form floating surfaces. So the first part of this the webinar today is about the CAD geometry and the CAD file formats, and Uday will...
Krish, I just want to interrupt quickly. There was a question, a very good question about what about parasolids in terms of the CAD file formats? Thanks for that question. Let me take that. Parasolids, definitely, if you have a parasolid format file, definitely that would be a very good format as well because parasolids is a solid model representation, so it's very similar. Actually, it's quite a bit better than step files because it's parasolid data, and we do read parasolid data. So that's also an important format that we haven't put up on the slide. Thanks for bringing it up.
Thank you, Joe.
Okay, so Krish basically went over the different types of geometry types, which is solid surfaces and meshes, and also he talked about the different file formats. Now I'm going to go ahead and show these to you in our CAD/CAM applications, how you can read these files, translate them into either you're running Visual CAD/CAM, or you could be running our plugin for Rhino, or you could be working within SolidWorks, and we'll take a look at the difference between each of these file types in here. So I currently have our flagship standalone Visual CAD/CAM application loaded in here, and as you go up to the Home tab in the ribbon bar and select Open, you will see that Visual CAD/CAM offers you a wide range of different types of file formats for translations in here. So you could bring in IGES files, step files, you have parasolids, you could read native Rhino files, SAT files, step, STLs, and a whole bunch of other file formats that can be translated into Visual CAD/CAM. So typically you would be receiving your CAD models from your engineering or design team or from your customers in one of these formats, and you could read these files into Visual CAD/CAM to program your toolpaths. And we'll also talk about how we can work with native files that could be created in Rhino and also SolidWorks. So Visual CAD native file format is VCP. So once you import a file or load a file and save it in Visual CAD, or you create a new file, create a drawing in Visual CAD and save it, that would be created and saved as a VCP format, which would be native to Visual CAD/CAM. So the first thing I'm going to go over is taking a look at an IGES file in here, and we'll show you the difference between the different types of file formats. So I'm going to go ahead and select this cavity part, an IGES file. I'm going to load it in. So IGES file basically represents a bunch of free-form surfaces, and as you translate these files into Visual CAD/CAM, you can see that each of these are individual surfaces. They're not connected. They could be sharing the same edge, but they are free-form surfaces. Now, to identify the type of geometry in here, in Visual CAD, you can go over to the Analyze tab up in the ribbon bar in Visual CAD, and then select Part Information, and this provides you information about the shells and faces. The faces are basically surfaces. So if you had a polysurface model, you would see that the number of shells would be probably 1, and then the polysurface could be made up of a whole bunch of surfaces. So you would see number of shells and faces. In this particular case, since we are working with an IGES file, it represents the number of faces as 15, and so as the number of shells. If you're
So
working,
just sorry to interrupt. The shells in our terminology really represents polysurface. So I mean, you can think of number of shells as equal to number of polysurfaces. So polysurface is a term that Rhino people use. Thanks, Uday.
thank you, Joe. So the meshes basically represent STL files or polygon meshes, so your facet data meshes. So if you had any mesh geometry that you imported in, it would be represented as number of meshes, and it will show you the triangle count on the mesh. So you could have one mesh with several thousands of triangles. The mesh could be made up of several thousands of triangles or millions of triangles. So this basically represents the number of triangles in a given mesh, and you can have one or more mesh geometry in a given file. Number of curves actually represents your 2D or 3D wireframe geometries, curves in the model itself, where it shows that it represents a number of curves. In this particular part I loaded has one curve geometry, and then we have about 15 surfaces or faces, as you can see. Now, to be able to program our 3-axis or machining operation, we would need to have solid surface or a mesh geometry. We will not be able to generate toolpaths for just curve geometry or a wireframe. Now, a curve or a wireframe geometry is where there is no surfaces or solids. It's just basically a bunch of lines and arcs and splines, a bunch of curved 2D or 3D curve geometry, which has no surfaces, or basically if you consider this as without being shaded in here, like a wireframe where this, you can't shade it. Even when you shade it, there's no solid surface geometry. You will not be able to machine to those geometries if it is just a bunch of curves for programming 3-axis machining operations. So you would need to have either a solid surface or a mesh geometry to effectively generate a 3-axis toolpath. So what we looked at here is an IGES model, and in this case of an IGES part, you can see that each of these are individual surfaces in here. So basically they're represented by individual surfaces. They could be sharing a common edge between the adjacent surfaces. Since they are not stitched or joined together, they don't form a poly surface. Now we'll take a look at the same example as a step model. So I'm going to go into Rhinoceros in here, and we'll take a look at that as a step file format. Now Visual CAD can also read step files. I just wanted to go over our plugins in different CAD systems, so that way our attendees can see in all the different systems in here. Now Rhino, when working with Rhino in Rhinoceros, you can use the native file format, which is 3DM, to create your geometries in Rhino, and then you can program toolpaths. So working in native format basically reduces or eliminates any translation errors. So it is best to work in native formats, whether you're working in Rhino or if you're working inside of SolidWorks, you would want to work it, model the part in SolidWorks and, use the native formats for programming your toolpaths. Using either Visual CAM for SolidWorks if you're running our plugin for SolidWorks, or if you're running inside Rhinoceros, which would be Rhino CAM. Now Rhino can also read a whole bunch of different file formats in addition to native formats. Rhino has an extensive list of file translators in here, and I'm going to load a step file into Rhino, the same part that we looked at in Visual CAD CAM. So as you import a step file, Rhino provides you with these import options which you could select from, and once you have the part imported, you will notice that this is basically a single polysurface geometry. When you make a selection of the geometry or you highlight the geometry, you'll see that in Rhino in the right above the command window it says one polysurface added to selection. To learn more about the characteristics or the properties of this particular geometry, you could go into Rhino and use the object description object properties command, and it'll tell you that this is a valid polysurface. It's a closed polysurface with 15 surfaces. So the same part what you looked at in Visual CAD, was made up of 15 surfaces. Since they were not stitched together, they were all individual surfaces. So over here, you're seeing that it's all stitched to form a closed poly surface, which forms a watertight model. So which means there are no open areas or open edges. So it forms a closed watertight model. So one of the benefits of working with solid models or closed watertight models is you can also take advantage of our feature detection and machining when you work with solid models. That's also a benefit in addition to being able to program tool paths in 2.5, 3, 4 axis or 5 axis. Working with solid models can also, you can take advantage of the feature detection and machining as well. Now, let's take a look at, some of the, downsides of working with just surface-based models where you may have some gaps or issues with surfaces in here. So I'm going to bring in an example where importing an IGES model, you will notice that there are several gaps in here. So I'm going to use this as an example, this particular part. This model is made up of over 247 surfaces in here, and if you zoom in and take a closer look at some of these areas, you'll notice that some of these surfaces are missing in here. So this could be due to a translation error when you export from one CAD system to the other. So depending on whatever CAD system this was modeled in, when you export, translation could cause issues where you might lose some pieces of information like geometries in here. You will notice that there's a surface missing around the fillet over here. There's also a couple of surfaces missing right over here on this edge in here. So if you use the show edge command, it'll basically represent where you have the open edges on the model, and you can see that there's open edges over here, and you can basically you would have to go back and fix these geometries in the native CAD system. Here it happens to be Rhino, so you may have to recreate surfaces. So you want to make sure that when you program your tool paths, your cutter doesn't dive into those areas in here. So typically when you have files that you import in IGES format, there could be some of these surfaces the edges may not be right on top of each other, so you might end up with large gaps, so which would result in the which would have issues in machining and result in the quality of the finish and the accuracy as well. So you will notice that some of the disadvantages is your surfaces may not connect well, which means the edges may not line up well when you're working with IGES files due to translation errors and translation issues that you might have. As you can see, there's a gap over here as well. So
let me interrupt here, Uday. As far as the gaps, you can think of the problems associated in machining. When you have such a large gap as like a fillet or an end fillet missing, the danger is it's so tiny that you miss it, and you run the machining operation. The machining operation will work fine, but if you're using a small enough tool, the tool could potentially go into that hole and down to the bottom surface, and then you have a lot of problems when you have something like that. That's your catastrophic or a pathological case. But even in cases where you have small gaps or small overlaps, what you're going to notice is tool marks. Because of the gaps, the cutter is just going to dip in slightly and come back out if the cutter is large enough so it doesn't fall in. So you're going to see at the end result of the machining is you're going to see tool marks on the surface. So it's very important. That's why Uday is suggesting that solid models with edge-matched surfaces or poly surfaces with edge-matched surfaces are the most important formats if you're very concerned about surface finish. Thanks, Uday.
Thank you, Joe. So we talked about solids. We looked at surfaces, like surfaces could be in IGES file format, or it could be even if you save a file, if you create model something in Rhino, you can explode the poly surface into surfaces. So when you save it as, Rhino can represent solid surfaces and meshes in their native 3DM file format. So you could have a combination of all three geometry types saved in a native Rhino file. Now the next thing we're going to take a look at mesh geometries, which could be STL files. Now these mesh geometries, the meshes could be generated from like a 3D scanner, or could be exported from a CAD system, so you could as an STL as well. So when you read in or import or translate a mesh file, you will notice that the the mesh, this geometry is made up of meshes. So as you go into a wireframe view, you'll be able to actually see the triangles, basically that's, that are formed for the mesh. So you can see that the facets on each of these, and the facet tolerance is controlled when at the time of export from the CAD system. So if you're using SolidWorks or one of the other CAD systems and you export it as a STL, you'd be able to control the resolution of the export of the STL, the number of triangles at the time of export in your CAD system. So you could be receiving files from your designers or your customers in a mesh geometry format, and we could still program toolpaths directly from mesh geometries as well. So you could be doing this in RhinoCam as well as in our standalone Visual CAD/CAM. So both these systems can handle meshes very well. Now meshes can also be commonly used in like scan data, like organic shapes. You could be basically working with mesh geometries that could have been generated from a 3D scanner, and you could still load these mesh geometries in and program toolpaths directly from mesh geometry. So if I display the mesh wires in here, you'll actually see those triangles on the mesh geometries. And these basically, when you look at the object properties, it tells you it's a valid closed double precision mesh with so many vertices on the mesh, and you can get all the information about it. So if you load the same mesh geometry into Visual CAD/CAM, it represents a mesh and the number of triangles when you look under object properties in here. So for programming 3-axis toolpaths, we could be working in solids, surfaces, or mesh geometry. So now I'm going to go ahead and hand this back to Krish, who will be covering a few more topics, and then
just before you do that, can you talk a little bit about trim surface import? What is the format that we expect when we're importing in Visual CAD/CAM?
Sure, I will certainly do that, Joe. So when you export files from your CAD system, it could be, you may be working with Rhinoceros, or you could be working inside of SolidWorks. When you do an export as an IGES, you would want to consider exporting it as an IGES, and then you want to select the IGES file format. There's an option to pick, and you would want to pick IGES type as 144, which is basically a trim surface option. So you could choose IGES 144. There's IGES 143, 144, and several other formats. Trim curves or trim surfaces is the best option to export it from your CAD system and then read them into Visual CAD for importing IGES files. Now you have the similar options in SolidWorks as well. When you save a file, you can go into IGES and then pick options and choose export type as 144. If you're exporting it from other CAD systems like Inventor, or if you're using CATIA or any other systems, you will find similar options as well. So when you choose your IGES file format, you can go over to options and then make sure you select trim surface type for representing it instead of 143 or 186. You'd want to pick IGES type 144 for exporting, and this basically gives you the best translation when you read IGES files into Visual CAD/CAM. Now as far as step file format goes, we have AP203 and AP214 file formats, and you could be using either one of the file formats when you translate the files into Visual CAD/CAM. So both file formats should work. You should be able to translate your files fairly well into Visual CAD/CAM. If you're noticing any translation errors or issues, you may want to try one of the other formats. It could be just specific to the geometry. You might be noticing a translation error, so you could use IGES or STEP with one of the STEP formats. So I'm going to turn this back to Krish.
So the next topic that we will discuss is the effect of machining tolerances. And tolerances play a vital role in machining accuracy. It could be based on the machine tool limitations. There's geometry tolerance of the host CAD system. There's global tolerances that are associated with the toolpath. and arc fitting tolerances, where you want to fit arcs as you're creating your toolpaths. And we will walk through all of these in the demo, but a couple of things I wanted to mention here. One is I had forgot to mention earlier that we have published a blog on this webinar topic. So you have a lot of reference material in the blog as well, and we will make the location of the blog available to you as well. And when you go through the blog, you will see a lot of this summarized in the blog along with best practices. And so some of the best practices in terms of machining tolerances would be to make sure that you check all of your tolerance settings. And you might need to adjust some of these tolerances based on your requirements. And so that is something to keep in mind while Uday will walk you through some of these specific tolerances. It's something for you to keep in mind that you can also adjust these to your needs. Now, I won't go into a lot of detail about the calculations and, for example, our application uses double precision, which is 14 decimal places. So there's a lot more information in the blog, which I won't necessarily go through today during the webinar, but please do use the blog as a reference.
Thank you, Krish. So we'll talk about how the tolerances affect in file translation. Also, we'll talk about the tolerances affect in your machining, as well as your tolerances for arc fitting, as Krish pointed out in the slide. Now, first we'll talk about the tolerance for importing geometries into CAD. We're going to take a look at that first in Visual CAD/CAM, and then we'll also talk about Rhino and also SolidWorks. Now, in Visual CAD, we have a setting called part faceting tolerance. So when you import or load a file, a solid or a surface-based geometry, which could be a NURB surfaces, or it could be a solid like a step file or a parasolid or a SAT file format that you read, Visual CAD uses what's called part faceting tolerance to translate the geometry. So if you go under options, now the options can be located on the home tab, and you can select options, or you can find it right under the status bar. We can get to options. As you go into options, you will notice that there's a setting for tolerance and units. So Visual CAD has a setting for part faceting tolerance and also a curve hookup tolerance. Now the part faceting tolerance, this information is basically used when you import a file like an IGES or a step or any solid surface geometry into Visual CAD. Now the part faceting tolerance does not apply to importing mesh geometries because the tolerance is already set at the time of export in the CAD system. So now when you're working with a solid or a surface geometry and you load a file like an IGES file, which I've loaded in here, these tolerance settings are used for the file translation. Now as you take a look at the file, here I have the display type in the file set to flat shading. As you import the file, if you notice the translated file has large facets. Now this facet information is used for establishing your toolpaths whether you're programming a 3-axis or a 4-axis toolpaths. If you see larger facets on this part, when you program the toolpaths and machine the part, you would basically notice these on these machine parts as well. So you would want to make sure before you start programming your toolpaths, you would want to import the file in a tighter tolerance to reduce these facets, so that'll improve the finish, the surface finish on the part as well. So one of the ways to accomplish that would be to go into your options, and you can tighten up the tolerance in here. So since I'm working in inch units, the default is set to 2000s. I could set it to 1000s, or I could even go tighter, 1/10 of 1000s, depending on the complexity of the model, the size of the part you're working on, and then the features that you have on the part. So as you tighten up the tolerance, you would actually want to go back and reopen the file or re-import the file in here. So I'm going to go back and reopen the file, and you will notice that upon loading the file, the translation time could increase. Also, you'll see that the surface has show much, they don't show these large facets, what you noticed earlier. So importing or translating the file with a tighter tolerance helps you in improving the quality of finish on the machine parts. It improves the surface finish as well. So you would want to look at first step when you're working in visual CAD/CAM is as you load the part, you want to check your part faceting tolerance to see if you imported it at a good tolerance or tight enough for for the accuracy and the surface finish that you're looking to accomplish on the part that you're looking to machine. Now, in Rhino and SolidWorks, we actually use the machining tolerance is what's used to determine the surface finish of the part. So the importing of the CAD geometry, the CAD model facet facet information or facet tolerance is not applied or not being used in Rhino and SolidWorks. So as you program or generate your toolpaths, the tolerance that you define in each of these operations is what controls the surface finish and the accuracy of the the quality of the surface finish that you accomplish. And you have these settings under global parameters in each of these operation types, whether you're programming 3-axis, 4-axis, or any axis. So today's webinar is focusing on 3-axis, so you'll notice that the global parameters has the options to establish these tolerances, which will actually control the surface finish and the tolerance that you can set for programming your toolpaths. Now the same thing also applies in SolidWorks as well, where you can establish the where the CAD model, the tolerance of the CAD geometry is not taken into account. So the tolerance for machining can be controlled in the actual operation itself as you program the machining operation, whether you're programming a roughing or a finishing operation. Now let's talk about the tolerance for arc fitting. We talked about in the toolpath, so I'm going to go ahead and program a toolpath in here. So first step I'm going to do is program a roughing operation, and I'm going to select a tool. I'm going to pick a 3/4 inch end mill, and I'll go ahead and generate a toolpath in here. Now I'm programming this toolpath with just the default tolerance settings that are in here, and as you notice, the tolerance for the the global parameters is set to 1,000. Now for arc fitting, it is recommended that you would want to use your arc fitting tolerance to be 2 times of your global tolerance. So whatever you have set for the global tolerance, your in tol and the out tol, if it's set to a 10 thou, you would want to set your arc fitting tolerance to 2 times that. So that will result in a best arc fit result on the toolpaths. Now you might be wondering what the arc fitting is and how does it affect. So as you take a look at these toolpaths in here, these arcs are being fitted to the linear motions that are generated on the toolpath. So for best arc fit results, you'd want to set the arc fitting tolerance to be 2 times your global tolerance. So setting the arc fitting tolerance much slacker than the global tolerance could cause the the arcs to be deviating from the actual geometry. So you would want to make sure that the arc fitting tolerance is set as a general practice. Best practice, you would want to set the arc fitting tolerance to be 2 times of your global tolerance that you set. Now you can also specify your tolerance under global parameters. You have the in tol and the out tol parameters. Now for roughing operations, these are by default set to 10 thousandths for in tol and the out tol. So basically in tol represents how much you can cut into the net shape, which is basically into the I would call it the into the stock material. So if you have the slacker the tolerance, you will notice that the toolpaths what are generated in here, you'll see that you have larger chord segments in here as the tolerances is slacker. The tighter the tolerance, you will notice that you will end up with more number of go-to motions, so which means more number of points between each motion. So if you take a look at the information in the toolpath here, you have a little over 2,000 go-to motions on this particular roughing operation that's programmed. If I go back in here and tighten up the tolerances, so let's say I tighten this up to 1,000ths, and since I tightened up this to 1,000ths, I'm going to go back into the arc fitting tolerance and set this to 2 times of my global tolerance. Now as I generate the toolpath, you will notice that this adds more additional number of go-to motions. As you can verify this by going into information, you'll see that it's jumped up to close to 3,000 go-to motions in here. And as you examine the toolpaths, you will see that the distance between each motion is much shorter or much smaller, resulting in a higher accuracy, and basically the in-tall settings and the out-tall settings basically allows you to control the tolerance to keep basically to allow you to how much you can cut into the net shape, or basically it's the in-tall represents the maximum thickness of material that can be removed from your stock layer. So you can control these parameters for each of these operation settings, and these settings are available in roughing and finishing operations in each of your 3-axis operations that you're looking to program. So with this, I'm going to go ahead and switch it back to Krish. He is going to go over a few more slides, and we'll try to switch back into the product and go over the different settings.
The next topic we wanted to discuss is the role of stock to leave. And Uday briefly touched upon stock and the net shape. So the stock to leave is something that you can utilize based on your requirements. You can adjust the stock to minimize the amount of material that needs to be removed. So for example, being a subtractive manufacturing process, it's all, the machining operation is all about removing stock. And so your control geometry can be used to contain the tool path and also to limit the amount of stock removal. You can also adjust the stock values. You can have negative and positive stock values, and Uday will show an example of this to achieve required fit. And you can also use the stock value in terms of finishing operations. Generally, it's good practice to leave the stock value at 0, but you can also use the stock value in finishing operations. For example, you can use it for roughing or pre-finishing by simply adjusting the amount of stock to leave. So the role of stock to leave is a pretty important role when it comes to your settings, and Uday will walk through and demonstrate some of these to you.
Thank you, Krish. So we'll take a look at how we can specify stock to leave in each operation types, which is going to help us in going from a roughing to a pre-finishing to finishing operations. Now, typically, when we program roughing operation, by default, you would be specifying a stock to leave on any roughing process. So this process of roughing, which is called roughing in layers or roughing in levels, we're going to talk about that in a few slides down the road. So in a roughing process, typically you'd want to leave some material above the part surface so you can then go back and create finishing and pre-finishing tool paths. Now, by default in the roughing process, the stock to leave is set to 25 thousandths. Now, this leaves uniform material in X, Y, and Z, since this being a 3-axis operation, so it'll leave a minimum of 25 thousandths in all the 3 linear axes. Now, as you program the tool path and simulate it, so I'm going to run a simulation here. I'll just do a simulate to end. You will notice that the roughing process has left stock in here, and you can see each of those stair steps. This is basically roughing in levels, and it's leaving a minimum of 25,000 stock. So this amount of stock that you're leaving can then be removed using pre-finishing and finishing operations. So ideally on a roughing process, you would be leaving some material so that that material can further be removed using subsequent programming operations. That could be different types of finishing operations that you could apply for finishing this part. So when you specify a stock to leave, it's going to honor the amount that you put in, and it'll leave the minimum amount of stock. It would be at least 25 thousandths being left. And as you can see in this process, we specified the stock to leave as 25 thousandths. Now, on a finishing process, you could be starting out with a pre-finishing or a finishing process where you can specify a stock to leave, and you could be programming finishing in multiple operations. So for example, if I program one of the finishing operations in here, and I'm going to pick a tool, or for example, I'll go with a 1/2 inch ball mill, and we'll specify to leave a stock of 10 thousandths in here. So this will leave a uniform stock of 10,000s above the part surface. So it's going to maintain, stay above the part surface by 10,000s, which gives you the ability to go back and finish it to the actual part surface. So you can specifying a positive stock will leave material above the part surface. Now you could have an application where you may want to overcut it, meaning you may want to have the machine part to be slightly smaller than the actual part. This could be an application where you need to apply some kind of a resin or a coating on top of the finished part, so you would want to overcut the part to shrink it. So you could specify a negative value for the stock under global parameters. This would result in overcutting it. So specifying a negative value in here will result in overcutting it, which means you're cutting into the part surface and you're shrinking the part by the specified stock value. So you're basically going by 10,000s, you're cutting into the part. So this could be like an application where you need to apply some sort of a coating or a resin so on top of the finished part, so that brings it back to the actual geometry of the part. Or if you have parts that needs to be fitting into tight tolerances, you may want to slightly shrink it rather than having to go back and modify your actual CAD geometry to have it resized or shrink it. You can actually do this in the operation itself, where you can specify a stock. Now, one thing to be noted here is the maximum value that you could set for the negative stock cannot exceed the tool radius. So in this particular case, we are using a 1/2 inch ball mill, so I can't set the negative stock amount to be larger than 1/4 inch. So that would be a mathematical limitation. So you can go, maximum you can set is your tool radius for negative stock.
Let me qualify that. Actually, the negative stock cannot be larger than the smallest radius in your tool. So if you're using a flat end mill, there are no radiuses in that tool, so you cannot specify a negative stock. But if you're using a ball end mill, then the smallest radius in the tool is equal to the tool radius, so you can go all the way up to almost the size of the tool for the negative stock. So, and if you're using a corner radius tool, then the negative stock cannot be larger than the radius of your corner. So that's an important distinction. It's not the tool radius per se, but rather than the smallest radius in the tool. I hope that makes sense. And you can read a little bit more about that in our blog, the best practices for 3-axis machining. Thank you, Uday.
Thank you, Joe. So the next thing is to how you can contain your tool paths to specific areas. So if you want to just rough within a certain area and not rough the entire stock extents, you could specify areas to restrict it by specifying containment boundaries. So one of the ways to accomplish that is using containment regions, or you could even use part surface selection to restrict or contain tool paths to specific areas. So for example, in this particular case, I can choose to only cut inside this area in here. I can select a containment, and the containment can be applied in all the different types of all the different types of 3-axis operations. So I could specify an area to contain, and I could go back and program that specific area with a smaller tool if needed, and then generate the tool path. So you can contain the tool paths to specific areas by defining containment regions. And we'll cover this in detail in the slides, and that we're going to cover in the coming slides in here. So with this, I'm going to hand this back to Krish, and he's going to cover a few more topics, and then we'll demonstrate that to you as well.
The next topic we are going to be covering is surface finish. And surface finish is dependent upon many factors. It's dependent upon tolerance, the stock material properties, depending on the type of material that you're machining, the tools that you're using, the cutting feeds that are employed, and the machine tool capabilities. So you will probably need to do a little bit of experimentation with the different tolerances and machining strategies to determine what to use to yield the surface finish that you desire. And again, in the blog, we have some best practices that you can look at But a couple of the best practices I'd like to mention here before I turn it over to Uday is, you normally want to use machining regions that contain your toolpaths to flow with the geometry of the part. And then you can also use different cut patterns and directions of cut to obtain better surface finishes, and Uday will talk about that as well. So this part of the demo is going to be focused on surface finish and how you can control your surface finish.
Thank you, Krish. So to get a better surface finish, and again, this depends on the type of toolpath methods you're applying here. So you could be programming using a combination of different methods in here. So for example, in this particular case, I'm going to go ahead and generate a finishing toolpath on this particular part. I'll pick a ball mill tool and generate it. So now as we generate the toolpaths, you might be noticing that when the toolpath, in this case it happens to be a parallel finishing operation, when the toolpath is generated in parallel planes, you would notice scalloping in some of these steeper sections on the model. So if you want to go back and clear up those areas, you would probably want to go back and run a parallel finishing operation from a different angle of cut or a direction of cut. And we'll cover the parallel finishing toolpath a little bit more in detail in the coming slides, and we'll talk about when to use each method. We'll cover that, but just to give you a quick overview of how to control the surface finish, you could be basically changing the direction of cut, the angle of cut, to eliminate some of the scalloping and to improve the surface finish based on the geometry and based on the toolpath operation and the strategies that you're going to be using. And also you can refer to the webinar that we had on feeds and speeds to how we can improve the how based on the material types and what type of feeds and speeds that you can set to basically to get optimal surface finish for the material based on the feeds and speeds as well.
Thanks, Uday. So we've talked about geometry, we've talked about file formats, we've talked about tolerances, surface finish, and so once you have all of this information you've gathered, you're now ready to look into what kind of a machining strategy that you want to use. And so some of the things that would come into consideration are, how large is the part? Is it going to fit on your CNC machine? Would you have to machine it in sections? Can you machine all of the features from one side, or would you have to flip the part over for secondary setup and secondary machining? And then, just relatively straightforward questions like if you're going to be cutting flat sheets or simple cutouts, you can probably just use 2.5 axis. You don't need to use 3 axis. On the other hand, if the part has tapered walls, then you would be using a 3-axis operation. So some of these considerations along with the geometry, the file formats, the tolerances, and the surface finish are what you would take into account before you decide what kind of an operation to use. And so in the next slide, we will talk about the different operations that are available in our standard configuration for 3-axis machining. So the first one we will talk about is the horizontal roughing operation. This is a bulk removal strategy, and it removes material in levels from the raw stock model. So it cuts in the XY plane at a certain Z level, and once that is completed, it moves on to the next Z level, and it repeats the procedure until the bottommost Z level is reached. And as Uday mentioned earlier, and we will talk a little bit more towards the end, you can also use containment strategies to make sure that the horizontal roughing operation is optimized based on the amount of material that you need to remove. We will also touch upon this one factor later, but I wanted to mention it here. There is an option called clear flats in your cut levels tab, and Uday will talk about that a little bit. But that can be used for clearing horizontal sections. And again, as I mentioned earlier, there's a lot of tips and best practices available in the blog as well. So you can reference that for the horizontal roughing operation. The next operation is the parallel finishing operation, which is one of the most common strategies for finishing. And this is best suited for parts that are more horizontal than vertical, because the cutter is restricted to follow the contour of the part while being locked to a series of parallel vertical planes. And so with parallel finishing, you're able to obtain a pretty good surface finish, and you can adjust the parameters, and Uday will talk a little bit about this operation as well in terms of how you can adjust the containment, adjust the parameters to obtain the results that you're looking for. The next operation is horizontal finishing, and in this strategy the cutter finishes in constant Z levels, and this is more suited for parts that have steep walls. Now, one thing to remember about horizontal finishing is if you have geometry which is very close to flat, you're going to notice that the tool paths, are further apart. And so we do have an option in that case called optimized machining, which Uday will touch upon, to be able to also take care of the flatter areas, since this horizontal finishing strategy is more suited for vertical rather than horizontal areas. Then spiral machining is the next toolpath method we wanted to talk about. It is a strategy that's best used as a finishing operation for regions that have circular characteristics. And the spiral cuts are generated inside a machining region extending from a center point. And once again, you have various methods to parameters to control how you want this toolpath to be generated. And this is also a strategy that is better suited for parts that are more horizontal than vertical. So similar to what I said about the horizontal finishing, if you are using spiral machining and you do have vertical walls, you might want to either contain the geometry, or you might have to come up with strategies to handle those scenarios as well, because spiral machining is more suited for horizontal than a vertical. And then the last operation I wanted to touch upon is the radial machining. Similar to spiral machining, this strategy is also used for finishing operations for regions that have circular characteristics. And in this type of strategy, the cuts are generated, linear cuts are generated extending from a center point within the machining region. Now, this can be used for both vertical and horizontal areas, and it works well in areas where spiral machining may not be the best option. And spiral and radial machining are often used together to maximize coverage and achieve a better surface finish. So these are the main operation types in our standard configuration: horizontal roughing, parallel finishing, horizontal finishing, spiral machining, and radial machining. And Uday will walk us through these operations now.
Thank you, Krish. Folks, you might have already noticed on some of these operations that we programmed a few minutes ago. So we talked about a few of these operations when we talked about tolerances and surface finish. So typically roughing processes are used where you need to remove bulk of the material from the stock. So the roughing operation automatically takes into account the stock that's being defined. So you could be starting with a rectangular stock like a box stock, or it could be any stock shape, any arbitrary stock shape that you can define. In our standard configurations, you could define box and cylinder stocks, and you can basically use a roughing operation where it automatically takes into account the stock that you define, and based on the tool that you specify in here, and the parameters that you set for the roughing operation, the toolpaths are computed. So you can specify your stock to leave, as we talked about earlier during the webinar. You can choose your cut patterns for the roughing operation. There's cavity regions and core regions. So the roughing operation can automatically determine what a core region is and the cavity. So in this particular part, you will see that there's a cavity in here, so it automatically uses the cavity cut patterns that you specify, and for core regions it'll use the core cut pattern. So when this option to use facing cut patterns for core region is selected, and you can control the step overs for each cavity and core regions, as well as the cut levels can be set for each of these. Like the step down can be set how much of material you want to remove per pass in Z. This can be controlled either based on a percent tool diameter, distance, or number of levels. And also, as Krish pointed out, selecting clear flats will go ahead and add an additional pass to clean up each of these flat areas or flat faces on the part. So when you select generate, this computes your roughing tool path, which is known as roughing in layers or roughing in levels, also known as Z-level roughing. So when the roughing tool path is generated, you will see that the tool path you can preview it in levels, and each of these Z levels can be viewed by selecting the Z-level display. And since we also had the clear flats selected in here, you'll notice that it's cleaning up each of those flat areas. And for the cavity regions, it's using the cavity cut pattern. And for the core areas, it's using the facing cut pattern. As you can see, the differences between the core and the cavity regions. Now, when you simulate the tool paths, you will notice that the roughing operation creates roughing in layers or levels, so you can see the actual part geometry as well as your stock geometry, which shows the different levels in each of these roughing operations that are generated. So this is known as roughing in levels or Z-level roughing. It's a very efficient way to rough, create your roughing strategy, and it can be applied to both core and cavity regions. Pretty much any 3D model, any 3D geometry that you have to program, your first step would be to program a roughing operation. Now, once you have a roughing operation programmed, you would then look at different types of finishing strategies. And one of the finishing strategies could be a parallel finishing operation, which is used for finishing areas that are not very steep. So parallel finishing is a great way to finish parts similar to these, where you do not have a lot of steep areas on the part, where you have areas that are not vertical or not very steep, and you can use parallel finishing. Now, this can be found under the 3-axis methods and parallel finishing. Now, this method is available in standard, expert, pro, and premium configurations. Folks, we are running a little bit over time, so we hope you wouldn't mind if we take a little bit more time, like 15 minutes over the schedule time, 9 o'clock, so we'll probably run until 9:15. So hopefully you will be able to stay with us till the end of the webinar. So with the parallel finishing operation, you will have the ability to set your, tolerances, the stock to leave. So if you want to leave in a material above the part surface, like we talked earlier, you can specify a stock to leave. And then you control your cut direction and the angle of cut. So you can set your cut direction to climb, conventional, or mixed. Your angle of cuts establishes the direction of cut. Now, by default, the angle of cut is set to 0, which means the tool path will run in parallel planes parallel to the x-axis. So your cut pattern will follow along the x-axis, as you notice it in here, the x-axis where you have the part oriented and defined your machine tool coordinate system. So by default, the angle of cut is set to 0. Now, when you are looking for a surface finish, and if you're noticing scallop due to machining from one orientation, so I'm going to go ahead and create a stock geometry in here and then run a simulation of this parallel finishing pass, and we'll take a look at the surface finish. And what we talk about is going back and programming a parallel finishing operation in another direction to remove some of these scalloping that you're seeing based on cutting in one direction in here. So you could go back and rerun a parallel finishing operation again, and you can change your angle of cut to go across from 0, which is 90 degrees, and I'm going to put in 90, and I can also specify a step over to be even tighter. You can specify the step over based on the type of surface finish you're trying to accomplish. You could use a percent tool diameter, a distance, or you could even specify a scallop height. And this can be set in here in the parallel finishing operation. Now, you will notice that with the parallel finishing operation, with the angle of cut set to 90, so the tool path runs in parallel planes parallel to your y-axis because it's 90 degrees about x. Now, when you go back and run your verification in here, you will notice that it's going to be basically running in across directions. So that'll basically eliminate any scalloping that you may have left from the previous process and result in a much, finer finish, improves the finish of the machine part. So you can use the parallel finishing operation to control your angle of cut, which is the direction of cut, and to improve surface finish. Now the parallel finishing operation can also be used as a roughing operation in certain applications, where if you just want to apply a single operation to program both rough and finish, you can use the option to specify multiple step downs, and this can be found under the Z containment tab, where you can set multiple step downs in parallel finishing, where you can control the step down distance either as percent tool diameter, distance, or number of levels. So this kind of works like a parallel roughing operation. You also have the ability to specify Z containments in parallel finishing, where you can specify highest and the lowest Z. For example, if you don't want to cut below a certain level in here, I can go back and pick a point, and you can restrict the Z on the parallel finishing toolpath not to cut below this level. So as you generate the toolpath, you will notice that the toolpath stays contained in the Z level based on the Z value that you put in for the Z containment. You can either graphically pick a point, or you can enter in a coordinate value based on where you establish your XYZ origin. So parallel finishing is a great way to finish parts where you do not have a lot of vertical areas or steep sections, and it's a great way to program pre-finish and finish on a wide range of parts, and this is just one of the examples for a parallel finishing operation. The next thing we're going to take a look at is how we can program parts that have steep areas, like vertical sections, like drafts or tapers on a part. And for that, I'm going to go over that in our plugin for Rhino. I'm going to go over that in Rhino CAM in here. So we use a method called finishing in levels, also known as horizontal finishing, and you can find this under the 3-axis methods. You'll find horizontal finishing, and you could specify a tool. Typically for horizontal finishing and parallel finishing, you'd want to use a tool that has a slight radius, either a corner radius tool or like a ball and mill. So in this particular application, I'm going to use a ball mill tool in here for the horizontal finishing operation. You would set your feeds and speeds and clearance similar to how you would establish in any other 2- and 3-axis operations. Your cutting parameters allows you to specify your cutting direction. So in this case, since it's a finishing in levels, the horizontal finishing, you can alternate between climb and conventional as you go between levels, or if you want to just do a climb cut, you can set it to climb. So there's no mixed cut in the Z-level finishing. There's mostly climb and conventional, which means the first cut level in the Z would follow a climb path. The next pass would be alternating to a conventional cut, so you would basically be alternating between climb and conventional for the cut direction. Now the cut levels tab allows you to control how fine you want it to step down in Z levels. Now this could be set as a percentage of tool diameter, distance, or number of levels. So the horizontal finishing is also known as finishing in levels or Z-level finishing toolpaths. You have the option to contain the cut levels, where you can specify your top of cut. You can also set the bottom of cut. So if you don't want to cut below a certain level, you can pick a point and you can specify how far down you want to cut. So basically you can set your top and the bottom cut containments. You can graphically pick them, or you can enter in the values for the cut level containments. And as Krish pointed out, we have the optimized machining operation option in here in the horizontal finishing. When you select optimized XY machining, in addition to finishing in levels in these steep areas, you can also machine these near flat sections in one operation, so you don't have to go back and program multiple different operations with horizontal finishing. So when you generate the toolpath, you will end up with the horizontal finishing toolpath in levels in here. You can see your Z-level finishing, so it basically does uniform constant Z-level finishing, and with optimized selected, it automatically also finishes these near flat sections between levels as you step between levels. Now with the horizontal finishing and parallel finishing, you can also select areas to contain or limit tool paths. One of the ways you could select is by specifying a containment region. So in this particular example, I have the containment region selected around the periphery of this part in here. So by selecting this as a containment region, your tool path would stay contained to this area and not cut past this area. So the tool tip stays right up to that region that you select as a containment. So selection of containment regions is one of the ways to contain your tool paths. You can also select part surfaces as your areas to machine. So you can pick a bunch of surfaces or a handful of surfaces to like program, and I'm going to cover that in one of the other examples when we program one of the other type of toolpath methods. So both in horizontal finishing and parallel finishing, you can use containment regions to contain tool paths to specific areas, and the tip of the tool will stay up to that region. So horizontal finishing is a great way to finish areas that have steep sections. You could have drafts, tapers, and also if you have areas that have flat areas in between, like for example, if you have a pocket with a draft and the floor of the pocket is near flat, you can use the optimize option in the horizontal finishing to finish certain areas. Now the horizontal finishing and the parallel finishing can be both used as pre-finishing and finishing operations, and you can be using a combination of both of these methods for finishing. So we talked about the roughing, the horizontal roughing, which is roughing in levels or roughing in layers. We also talked about parallel finishing for areas that are not very steep, and for steep like vertical walls and steep areas, we looked at horizontal finishing. The next thing we're going to take a look at is how we can program circular regions where you have circular features like that you can use different types of machining methods in addition to parallel and horizontal finishing. So for that, I'm going to cover an example where we're going to take a look at spiral machining, and then we'll take a look at radial machining as well. So I have an example in here where we're going to show how we can apply different types of tool paths. Now ideally you would want to start with the roughing process in here. So you define your stock geometry, and then you would start with a roughing or z-axis roughing or roughing in levels. So once your roughing process is completed, you would want to program a finishing operation. Now radial and spiral machining is also available in standard, Expert, Pro, and Premium configurations of our product. So I'm going to talk about the radial machining operation in here. Now for radial machining and spiral machining, you can select a part region. So in this particular step, we are talking about the spiral machining. So the toolpath creates a spiral toolpath. Basically, you have just one entry and one exit. It creates a continuous spiral, and you could pick a part region in here as your part region, or a curve or a surface edge. You can select, or you can even pick a part surface as your control geometry. You would then want to specify your tool for the spiral machining. Typically you would want to use a tool which has a radius, could be a ball mill, a corner radius tool for a spiral machining. Establish your feeds and speeds and clearance. And in the cutting parameters, you have similar type of settings for global parameters, similar to what you noticed in parallel and horizontal finishing. Now your cut direction can be set to climb or conventional, and then the start point for the spiral machining can be set to inside or outside, and the default is set to inside. So inside would be basically starting at the center and working its way towards the edge of the part, or the edge of the part region that you've selected. And generating the toolpath creates a spiral toolpath, and the toolpath is projected down to the underlying geometry in here. So spiral machining is ideal for machining areas that are not very steep. So if you have a draft on a part similar to this but not very steep like vertical walls, you could use spiral machining as the toolpath is, it creates a spiral toolpath and being projected down to the underlying geometry in here. So you can specify additional parameters to control the spiral path, and automatically it establishes the centroid of the part region that you pick to establish the spiral. But if you'd like to change the spiral center point, you can specify a center point for both spiral and also in radial machining. And you can also specify a minimum radius to leave. So if you don't want it to finish all the way down to the center, you could specify to leave a minimum radius of the center, and it's going to leave a minimum radius like 1/4 of an inch, so you stay away from the center by a radius of 1/4 inch in a spiral machining operation. You could also be selecting multiple regions like 2 concentric circles, for example, to contain the toolpath between 2 areas. So spiral machining can be used as one of the finishing methods for machining like concave and convex surfaces, similar to the example that's shown in here. This method can also be used as a roughing operation where you can specify a step down multiple levels, similar to what you noticed in parallel finishing, and also you can apply Z containments to specify high and the low Z values in spiral machining. So the next operation, the final operation that we're going to cover today is going to be the radial machining operation, and I'm going to go ahead and bring in an example for that, and we'll cover the radial machining operation as well. So the radial machining, the options that you see in radial machining is very similar to what you noticed in spiral machining. It's ideally used for circular parts. You could specify a part region as your a containment region for generating your radial machining toolpath. You would specify a tool for it. So I'm going to go with a ball mill tool. Typically, you would want to use a tool which has a radius to it. And then in your cutting parameters, you have the option to specify your cut pattern. You could do zig or zigzag for the cut traversal. You could specify your cutting direction to be either climb or conventional, and then the start point could be set to inside, or you could start from the outside, work its way in. And you also have the option to specify the minimum radius like we noticed in the spiral machining operation. Now the radial machining can be used for both steep areas as well as not too steep areas. Now if you notice here on this particular part, you have several steep sections or near vertical areas. Now had I programmed a spiral machining toolpath on these areas, you're going to see that on this particular areas on the model, it's going to basically right against those vertical surfaces on the spiral machining toolpath. So that may not give you the most desirable surface finish on these steep sections in the model, since it's riding on these vertical surfaces in here. So radial machining might be a better strategy to program the toolpaths as compared to the spiral machining operation. Now in the radial machining operation, you could also specify to leave a minimum radius of the center, where you can specify the minimum radius, and you can also pick a center point in radial machining if you need to. So in this particular case, since I'm programming an entire circular area, I've specified it to leave a minimum radius so that the toolpath, as it gets down to the center, the points are very closer. It might make it very hard on your machine to interpret those points, so you can specify minimum radius to leave and apply a different type of toolpath strategy in here to program around the center section of the part. So the radial machining again can be used for both steep and horizontal features. You can also specify Z containments and multiple step downs, similar to what we noticed in horizontal and parallel finishing operation.